Morning, good afternoon, good evening. Welcome back, everyone. The last lecture we built DQN from the ground up. We understood why tabular Q learning breaks, how neural networks replaces the Q table, and how experience replay and target network stabilize training. Today we go deeper. We are going to look honestly at what still goes wrong when you train DQN on real problems. How you measure whether your agent is actually improving, and then a set of algorithmic extensions that address the remaining weaknesses. This is your Professor T. Muhammad, Lecture 8, PhD AI 830 sequence of lectures, Deep Reinforcement Learning. This lecture is more practical than by the last one. By the end, you will understand not just what DQN does, but where it struggles, sparse rewards, training instability, overfitting, and you will know 3 concrete algorithmic improvements: double DQN, dueling networks, and prioritized experience replay. We'll close by looking at where these ideas get applied in the real world, from Atari benchmarks to robotics. Here's the plan for today. We have 4 sections. The first is a diagnostic section. We identify the 4 core failure modes that practitioners run into when deploying DQN beyond simple environments. The second section is about evaluation, which is surprisingly subtle in reinforcement learning and often done poorly in the literature. The third is the improvements section, where we look at 3 algorithmic extensions that have become standard practice. And the fourth covers applications, concrete domains where these ideas have landed. Each section is self-contained, but they are sequenced deliberately. Understanding the challenges motivates the evaluation choices, and understanding evaluation shows you why the improvements matter. And you have ever wondered why reinforcement learning papers sometimes look impressive but fail to reproduce a lot of the answer lives in the sections 1 and 2. Challenges. Even with experience replay and target network in place, training DQN in high dimensional environments is genuinely hard. This section is about being precise about why. There are 4 distinct failure modes. So, as I mentioned, there are 4 distinct failure modes, and they each have different causes and different fixes. Conflating them is a mistake. If your agent is not learning, you need to diagnose which of these is the culprit before you start tuning hyperparameters randomly. The 4 challenges are the curse of dimensionality, sparse rewards, training instability, and overfitting. We saw the first one briefly in lecture 7, but here we treat all 4 seriously. Real world DQN implementations routinely encounter all of them simultaneously, which is part of what makes deep reinforcement learning so difficult to debug in practice. We touched on the curse of dimensionality in lecture 7, but let's make it concrete for the kinds of problems DQN is actually used on. An 84 by 84 RGB game frame contains over 20,000 values. The set of all possible such frames is effectively infinite. No table can enumerate it, and no agent can visit more than a vanishingly small fraction of it during training. Function approximation is not a nice to have, it is the only approach that can possibly work at this scale. The problem compounds in two directions. First, continuous action spaces, robotic control, autonomous driving, and physical system can't even be discretized without losing critical precision. Second, multi-agent setting. Multiply state and action spaces together across all agents. Two robots with 100 states each don't have two-dimensional joint states. They have 10,000. These scaling properties are what make function approximation with deep networks and default starting point for all serious reinforcement learning research today. Now let's look into sparse rewards. These are one of the most practically painful problems in deep reinforcement learning. The issue is that in many real environments, the agents only receives a reward signal at the very end of a long sequence of actions. Win or lose, goal reached or not, every action in between has reward zero. The Bellman backup has to propagate that signal backwards through potentially thousands of steps, and the further back you go, and weaker the noisier the gradient signal becomes. The classification of the classic failures case in Montezuma's Revenge, an Atari game where a random agent almost never encounters a reward at all. If you never see a reward, your Q values stay near zero. Everywhere, your policy never changes, and training makes zero progress. Training instability in DQN has a precise theoretical cause that Sutton and Bartow called the deadly triad: function approximation, bootstrapping, and off policy learning. All three at once. Each of these is fine on its own. Combined, they can provably cause divergence in the worst case. DQN's engineering fixes the target, network, and replay buffer tame this empirically on most tasks, but they don't provide convergence guarantee. The mechanism is this: bootstrapping means our targets depend on our own Q value estimates, which we are simultaneously updating. Small errors in those estimates don't stay small. They get bootstrapped back into future targets, amplified, and bootstrapped again. This feedback loop can send Q values to positive or negative infinity within a few thousand gradient steps. On top of that, consecutive transitions from the environment are temporarily correlated, so naive online updates cause the network to oscillate rather than converge. Experience replay addresses the correlation problem, the target network addresses the moving target problem, but both are engineering heuristics, not theoretical solutions. Overfitting in reinforcement learning looks different from overfitting in supervised learning, but it is just as damaging. In supervised learning, you overfit to your training set. In reinforcement learning, you overfit the specific transitions and states that happen to end up in your replay buffer. The network becomes excellent at estimating Q values For states it has seen many times, but wildly wrong, becomes excellent at estimating Q values. For states it has seen many things. So in practice, this shows up as an agent that performs well during the training but collapses as soon as you change anything about the environment. A different starting position, a slightly different level layout on a new random seed. Evaluation. Now let's look into this together in more depth, measuring whether your agent is actually learning. Cumulative reward, the total discounted return averaged over evaluation episodes, is that primary objective that reinforcement learning formally optimizes, so it is natural first a thing to measure for Atari. The community typically reports the human normalized score, or HNS, which is computed as the agent's score minus the random baseline divided by the human score minus the random baseline times 100. A score of 100% means human level. Anything above that is superhuman. The normalization is just because raw scores vary by orders of magnitude across different Atari games. Learning curve plots mean episode return on the y-axis against total environment steps on the x-axis. It is the standard visualization in reinforcement learning. So this is a profound thing I would like to repeat myself here. A learning curve plots mean episode return on the y-axis against total environment steps on the x-axis. It is a standard visualization in reinforcement learning papers, and it tells you two things: how much the agent improves over training and how sample efficiently it gets there. Sample efficiency, the number of environment interactions needed to reach a given performance level, is often more important than asymptomatic performance, especially for real world applications where environment interactions are expensive. Stability is what separates an algorithm that works from one that works sometimes. A method that achieves a high mean returns across seeds but with enormous variance is not actually reliable. You would never want to deploy it in real system where you need predictable behavior. Variance across seeds is first order metric, not an afterthought. There are two dimensions of stability worth measuring separately. The first is across run variance. Given the same algorithm and tasks, how different are outcomes across different random seeds? The second is sensitivity to hyperparameters. How much does performance change when you vary the learning rate, replay buffer size, target network update frequency, or epsilon schedule? A robust algorithm should degrade gracefully as you move away from the optimal hyperparameter setting, not collapse entirely. A third thing to monitor during training is catastrophic forgetting, whether the agent's performance on earlier parts of the task degrades as it continues learning. If you see the learning curve rise and then fall significantly, forgetting is likely the cause. Generalization is the hardest evaluation criterion to satisfy and one of the most commonly skipped in published work. An agent that generalizes is one that performs well on states and situations it did not see during training, not just the ones it did. This seems obvious, but the standard Atari evaluation protocol actually fails to measure it. Agents are trained and tested on the same game and with the same ROM, which means memorization of specific state sequences can masquerade to learning. Now, the good part, we have diagnosed the problem and we know how to measure them. Section 3 is about the three algorithmic extensions to DQN that have become standard components in any serious deep reinformation learning, or sorry, pardon me in English. Let me repeat it. Section 3 is about three algorithmic extensions to DQN that have become standard components in any serious deep reinforcement learning implementations. Dueling networks, which restructures the network architecture to learn state, value, and action advantage separately. The prioritized experience replay, which makes smarter sampling decisions to get more learning signal per gradient update. Standard DQN has a systematic bias problem. When we compute the Bellman target, we take the max over q values in the next state y equals r plus gamma times max over a prime of q of s prime comma a prime. That max operator is the problem. The q value have estimation noise in them, and taking the max over a set of noisy estimates consistently picks the one with the highest noise, not necessarily the one that's truly best. This is called overestimation bias, and it compounds through bootstrapping. Overestimated q values get backed up into earlier state, inflating q values everywhere. The dueling network architecture asks a simple but powerful question. In many states, the choice of action barely matters if you are in an empty corridor in a game. Whether you turn left or right has the same expected value. Standard DQN still has to learn separate Q values from each action independently, which is wasteful. Dueling networks separate the network into two streams, one that estimates the state value V of S, how good is this state regardless of action, and one that estimates the advantage A of S, A, how much better is this action compared to the average. The two streams are combined at the end to produce Q values, but the subtraction of a mean advantage is important. Without it, the decomposition is not unique because V and A can shift and by any constant while keeping Q the same. Subtracting the mean enforces identifiability. The key practical benefit is that V of S gets updated from every single transition, regardless of which action was taken. In standard DQN, only Q value for the action that was actually taken gets update per step. By learning V separately, dueling networks extract more signal from each experience and converge to better value estimates faster, especially in states where most actions are roughly equivalent. Standard experience replay samples transitions from the buffer uniformly at random, but not all transitions are equally informative. A transition where the agent's bellman Error is large where its Q value prediction was very wrong, contains more gradient signal than a transition it's already learned to predict accurately. Prioritize experience replay, or PER, exploits this by assigning each transition a priority proportional to its absolute Bellman error, the sampling proportionally to these priorities. DeepMind's Rainbow paper from 2017 asked, what happens if you combine all the DQN improvements at once? They took 6 extensions: double DQN, dueling networks, prioritized replay, multi-step returns, distributional reinforcement learning with C51, and noisy nets, and combined them into a single agent. The results significantly outperformed any individual component on the Atari 57 game benchmark and established a new state of the art at the time. The final section is about where these ideas actually land in practice. Deep Q learning is not just benchmark algorithm. It and its extensions are actively used in commercial and scientific applications across robotics, games, AI, resource management, and autonomous systems. Understanding the application landscape helps you see which challenges from Section 1 are most relevant in which domains and which extensions from Section 3 get used most often in practice. So the Atari 2600 benchmark has been the proving ground for deep reinforcement learning since DeepMind's 2013 paper. The setup is deliberately minimal. The agent receives raw pixel frames at 84 by 84 resolution, observes the changes in game score and its reward, and must learn a policy entirely end to end, but no handcrafted features. The suite covers 57 games spanning widely different challenges, reaction speed games like Pong, long horizon planning games like Pitfall, maze navigation, shooting, and more. The diversity is what makes Atari useful as a benchmark. An algorithm that does well across all 57 games can't be specialized to any particular skill, but Atari has known limitations that the community has increasingly acknowledged. Some games can be nearly solved by exploiting deterministic patterns in the game engine, which is why stochastic frame, skips, and sticky actions, where the previous action is repeated with some probability, were introduced to make the environment genuinely stochastic. Games like Montezuma's Revenge and Pitfall remains effectively unsolved by the standard DQN variants, exposing the sparse reward problem in its most extreme form. And performance on Atari does not always predict how well an algorithm transfers to physically grounded tasks. Robotics is where deep reinforcement learning meets physical reality, and the enduring challenges multiply. The most common approach is sim to real or simulation to real transfer. Train the agent in a fast physics simulator where you can run millions of environment interactions cheaply, then deploy the learned policy on real hardware. The gaps between simulation and the real world, differences in friction, actuator noise, sensor delay, visual appearance, is called the sim to real gap, and bridging it is an active research area. Domain randomization is the primary technique. Randomized physics, parameters, textures, lighting and camera positions during simulation training so the agent learns to be a robust to a wide range of conditions rather than overfitting the simulator specific parameters. So let's bring it all together. The central message of this lecture is that DQN is a powerful and practical algorithm, but it is not a plug and play solution. The four challenges, dimensionality, sparse rewards, instability, and overfitting, are real and require deliberate engineering to address. Understanding which challenge you are facing in a given application is the first step to fighting it, and that requires the kind careful evaluation we covered in section 2. The three algorithmic improvements, double DQN, dueling networks, and prioritize experience replay, are not exotic research ideas. They are standard components you should include by default in any serious DQN implementation. The rainbow result tells us that combining them is better than using any one alone because they address orthogonal failure modes. If you take one practical lesson from today, don't implement vanilla DQN for a new problem. Start with rainbow or just closest open source equivalent. Evaluate rigorously across multiple seeds and then diagnose from there. That's the workflow that the research community has converged on, and it will save you a lot of time debugging problems that have already been solved. Happy learning. See you in the next lecture. Be well.